Hello, this is Dr. Ren Hand, and this lecture will cover sections 2.2 and 2.3 in your textbook, and will address the topic of intelligent agents and control in cyber systems. And these slides are available in the D2L site for you to download as well. So first, we'll talk about agent architectures. When we talk about an intelligent agent, it's tempting to imagine a neat pipeline where the system first perceives the world, then reasons carefully about what to do, and finally takes an action. That sounds logical, but in practice, it doesn't work very well. The main problem is time. High-level reasoning takes much longer than many real-world situations allow, as far milliseconds can matter. Another problem is that perception itself depends on what the system intends to do. What data is relevant changes depending on the goal. So rather than thinking of agents as a simple perception, reason, action chain, we need architectures that are faster, more flexible, and more tightly coupled to action. A more effective approach is hierarchical control. Instead of one monolithic decision maker, the agent is organized as a hierarchy of controllers operating at different levels. Each controller sees the layers below it as a kind of virtual body. It receives simplified percepts from them and sends commands downward. The key idea is that lower level controllers run much faster and handle immediate reactions, while higher level controllers reason more slowly and strategically. This allows the system to respond quickly to urgent situations without giving up longer-term planning and goal-directed behavior. So who is actually in control in cyber defense? So this raises an important question for cybersecurity. Who is actually in control? Automation often decides faster than humans ever could, especially when dealing with high volume network traffic or rapid attacks. Humans still set the rules, but they may not fully understand how those rules play out in every situation. Control is not centralized in a single person or component. It is distributed across layers of automated systems, configurations, and policies. This distribution possible, but it also makes responsibility less obvious, which is something we'll return to later when we talk about ethics. Now, this diagram shows a generic hierarchical architecture. It's a hierarchical robotic system architecture. At the bottom is the environment, which the agent interacts with. Above that are low-level percepts and commands, which deal with immediate sensing and action. Higher up, percepts become more abstract and commands more strategic. Memory exists at multiple levels, allowing the system to retain information over different timescales. The important takeaway here is not the specific labels, but the structure itself. Each level simplifies the world for the level above it, allowing complex behavior to emerge without overwhelming any single component. And this slide shows functions implemented in a layer. So each layer in the hierarchy typically implements three kinds of functions: memory, percept processing, and action selection. The memory function updates internal state based on what the system has observed and done. The percept function transforms raw inputs into something meaningful at that level of abstraction. The command function decides what action to take given the current percepts and memory. And importantly, these functions look similar at every different. And this structural similarity is part of what makes hierarchical control scalable. And now we'll talk about when speed matters more than certainty. So this slide highlights why hierarchy is so important in practice. Some actions need to happen in milliseconds, like packet filtering. Others can take seconds or minutes, such as terminating sessions or isolating a host. Human review often takes hours. If every decision had to wait for the highest level of certainty, the system would fail catastrophically. Hierarchical control accepts that lower layers will sometimes act with incomplete information. Higher layers think more slowly, and that is intentional. The system is designed so that speed and certainty is not available. So now we're going to look at an example of a delivery robot. At first glance, this delivery robot example may seem far removed from cybersecurity, but it's doing exactly what any intelligent agent must do. The robot has very limited actions. It receives imperfect information from a simple sensor, and it operates in a dynamic environment where obstacles and goals can change. Importantly, it is not reasoning deeply about the entire world at every step. Instead, it relies on a structured control system that allows it to move, avoid obstacles, and follow a plan without stopping to deliberate constantly. This example gives us something concrete to think with before we translate the ideas to cyber systems. So this slide shows how the robot's behavior is decomposed into layers with distinct responsibilities. One part of the system focuses on following a plan, another focuses on moving toward a target while avoiding obstacles, and another deals with immediate sensing and steering. No single component understands the entire problem. Each layer handles a manageable piece of the task and communicates with the layers above and below it. This decomposition is what allows the robot to behave intelligently without being overwhelmed by complexity. And it's the same design strategy used in many real-world autonomous systems. And now we can map this directly to cybersecurity. So this is what a mapping from the delivery robot to a SOC analyst would look like. If you replace the robot with a security operations center or SOC, the analogy becomes clear. Obstacles correspond to malicious activity. The robot's whisker sensor is like an IDS or EDR signal. The target location represents a security objective, such as maintaining availability or stopping lateral movement. The plan becomes an incident response playbook. So just like the robot, a SOC cannot reason deeply about every event in real time. It relies on layered control, automation, and abstraction to function at scale. And so this brings us to belief states and the question of what should be in an agent's belief state. An agent does not decide what to do based only on what it sees at the current moment. It decides based on what it believes about the world, given what it has observed and remembered. A purely reactive agent has no belief state and tends to perform poorly in complex environments. On the other hand, an agent that relies only on internal models without perception also fails. Effective agents maintain a belief state that represents their best current understanding of both themselves and their environment, even though that understanding is always incomplete. And so the next important point is that cyber systems do not see the world, they infer it. So in cybersecurity, this idea is especially important. Cyber systems never directly observe an attack. They observe logs, alerts, traffic patterns, and behaviors. From those observations, they infer beliefs such as this host is compromised, or this traffic is malicious, or this user is a threat. These are beliefs and not facts. They are conclusions drawn under uncertainty. Automated systems act on these inferred beliefs because waiting for perfect certainty is not an option. Understanding this distinction between observation and belief is critical for evaluating both the effectiveness and the risks of automated cyber defense. So now we're going to talk about how autonomous response is a moral decision. Up to this point, we've talked about architecture, speed, and belief state as technical design choices. But once a system takes autonomous action, those choices become moral decisions as well. When an automated system blocks a connection or isolates a host or disables an account, it is choosing between competing harms. Acting may prevent an attack, but it may also disrupt legitimate users or business operations. Waiting may reduce harm to users, but it increases the risk of compromise. The key point is that autonomy doesn't remove ethics from the system. It embeds ethics directly into technical behavior. And so this concern isn't limited to cybersecurity. In 2016, President Barack Obama raised the question of moral context of self-driving cars. The technology can make fast, effective decisions, but the harder question is what values we encode into those decisions. When a machine must choose between two harmful outcomes, someone has already decided which harm is more acceptable. So the machine is not neutral. It is executing values that were designed into it, whether intentionally or not. And you can read the complete quote here from President Barack Obama, where he gives an example of what that decision could look like. And next, we'll talk a little bit about moral machines using the example of the trolley problem. So this is a famous hypothetical situation used to describe this kind of moral dilemma. So the moral machine experiment with the trolley problem makes this issue concrete by presenting people with trolley-style dilemmas involving autonomous vehicles. Millions of participants were asked. So applying the classic runaway trolley experiment, which I guess basically you can look it up if you're not familiar with it, but basically if a trolley goes down one path, it's going to kill, say, one person. If you switch it to the other path, it's going to kill 3 people. And so the question is, what would be the correct or moral decision in that case? That's one way the trolley problem is presented. If you look it up and read about it, you can probably see more examples. So applying that to decisions and dilemmas involving autonomous vehicles, millions of participants were asked what a self-driving car should do when harm is unavoidable. The results show that while some preferences were widely shared, others varied significantly across cultures. Importantly, these scenarios assumed perfect clarity about outcomes, but in the real world, systems act under uncertainty. That makes the ethical problem harder, not easier, because decisions must be made without knowing for sure what the consequences will be. So then applying the idea of moral machines to cybersecurity again, when we translate this idea to cybersecurity, the parallels are clear. An automated defense system may have to choose between protecting the organization and protecting individual users. It may prioritize availability or security depending on how it is configured. Automation increases speed and scale, but it also obscures accountability. When something goes wrong, it is not always obvious whether the responsibility lies with the software, the designers, the administrators, or the organization that approved its use. These are not abstract philosophical issues. They are practical governance questions that can be applied to any type of scenario in cybersecurity work. So finally, regarding moral machines, we'll talk a little bit about some issues and implications. The key takeaway from the moral machines work is not that we can find a single correct answer and program it into systems. Some values may be widely shared, but others are context dependent and controversial. In cybersecurity, this means that automated systems should not silently encode assumptions about acceptable harm. Decisions about autonomy, escalation, and response thresholds should be made deliberately, documented clearly, and reviewed over time. Hierarchical control gives us powerful tools, but it also places responsibility on humans to decide how those tools are used. So now we'll wrap up by talking about how we go from architecture to responsibility. And basically, we've moved through a full chain of ideas in this lecture. We started with agent architectures and why simple perception, reason, action models fail in real systems. We then looked at hierarchical control as a way to balance fast reaction with slower strategic reasoning. From there, we focused on belief state and the fact that cyber systems do not see attacks directly. They infer what is happening and they act under uncertainty. Once systems are allowed to act autonomously, those technical design choices become ethical decisions. Every automated response reflects assumptions about acceptable risk and harm. And so the assignment that you'll do this week asks you to take this entire chain seriously. You are not just describing a system, you're analyzing how control, belief, speed, and ethics interact in a real cyber defense context. As you work on the assignment, think less about whether the system is right or wrong and more about how its design shapes the decisions that it makes. So basically, as you work on this assignment, I'm not looking for the right answer or a perfect system design. I'm looking for whether you understand how these pieces fit together. I want to see that you can identify control layers clearly, explain what the system believes based on what it observes, and recognize why speed sometimes matters more than certainty. When you get to the ethical question, I'm not grading you on your moral stance or opinion. I'm grading you on whether you can articulate the trade-off and recognize who is making the decision and who bears the consequences. So be concrete, be specific, and focus on how the design of the system shapes the decisions it makes. Good luck and reach out if you have any questions, and I hope you all have a good week.